The next trig results we're looking at are known as the T results. So whereas the other day we were looking at what we call double angles, you could think of this one as like half angles. What it allows us to do is to turn a trig expression into a polynomial, because sometimes that's easier to work with than the trig. So it all starts where we say, well, we're going to let T represent the tan of the, well, normally we say theta on 2 because that's the most common. It doesn't have to be theta on 2, just half the angle of what we're working with. So tan theta would now become the double angle, and the double angle we saw was 2 tan theta, in this case theta on 2, 1 minus tan squared theta, in this case theta on 2. So I'm using the double angle results. But now, because we've said T is tan theta on 2, that just becomes 2T on 1 minus T squared. So we've turned our trig expression into, well, an algebraic fraction. Once we've got that, we can draw up a right angled triangle and work out the other ratios. So if tan is 2T on 1 minus T squared, opposite over adjacent, bit of Pythagoras, we can work out the hypotenuse. So square both and add them. This will end up being T squared plus 1 all squared. So our hypotenuse is 1 plus T squared. And so we can read off that all of our relationships. So if we let T represent tan theta on 2, we can transform tan theta into 2T 1 minus T squared, sine theta into 2T on 1 plus T squared, and cosine theta into 1 minus T squared on 1 plus T squared. So they are known as the T results for obvious reasons. Now, as I said, it doesn't have to be theta on 2. Think of it as a half angle. If we let T equal tan theta, then tan 2 theta would be 2T on 1 minus T squared. If T was equal to tan 2 theta, then tan 4 theta would be 2T on 1 minus T squared. So it's the half the angle of what we're working with. All right. So we're going to prove this little thing. 1 minus cos x on sin x is in fact t. We can transform that just to be the pronumeral t if we let t equal tan x on 2. So let's sub in our t results. So x is double x on 2, so we can use our t results. We get 1 minus, cosine x, 1 minus t squared on 1 plus t squared. Sin x, 2t on 1 plus t squared. Now, fraction on fraction, we don't like that. Fortunately, the denominator is the same in both fractions, so if I multiply everything by 1 plus t squared, we'll get 1 plus t squared minus all of 1 minus t squared over 2t. Tidy the top up, we get 2t squared, which cancels, and sure enough, we've transformed our trig expression into an algebraic expression of just t. So now, if we want to do something like this, we want to simplify 2 tan 75 on 1 plus tan squared. Similar to an example we looked at the other day. It's tempting to look at that and think, oh, double angles. But remember, the double angle result was 2 tan on 1 minus tan squared, not 1 plus tan squared. Mind you, they've given us a hint by saying we're going to use the t results to do this. So if I let t be tan 75, in other words, theta is going to be 150 degrees, so double the 75. Okay, so 2 tan 75 on 1 plus tan squared 75 will become 2t on 1 plus t squared. And that is one of our t results. It's not a double angle result, but it is a t result. And that's the t result for sine. So sine theta, we've just said theta is 150 degrees. Sine of 150, second quadrant, so it's positive. Acute angle is 30 degrees. And sine of 30 is a half. So it turns out to be a half. Okay. We're going to prove this trig identity. I suppose the hint to use the t results here is that the fact that I'm going to prove it's tan theta on 2. So let's turn it into an algebraic fraction question. I'm going to say, all right, well, I'm going to let t equal tan theta on 2. So in our fraction, I'll substitute in the t results. So 1 plus 2t on 1 plus t squared minus 1 minus t squared on 1 plus t squared over 1 plus 2t on 1 plus t squared plus 1 minus t squared on 1 plus t squared. It looks awful, but again, notice the denominator is the same in everything there. So we'll just multiply by 1 plus t squared, everything, and we just got to tidy up our algebraic fraction. I get 2t squared plus 2t on 2 plus 2t, factorise and cancel, and we get t, but remember we said t is tan theta on 2. So yes indeed, this trig fraction does simplify down to be just tan theta on 2. So I guess there's an example of where turning it into polynomials or algebraic fractions makes the question a lot easier, because we're just playing with the algebra to come up with t, an HSC one. Again, they've given us the hint, use your t results. It does say or otherwise, so if for some reason you wanted to do it a different way, well, feel free, but they're not giving you this hint to try and trick you. They're saying, hey, this is probably the best way to do it. Cosec plus cot is cot theta on 2. Okay, cosec plus cot. Well, they're the reciprocal of sine and cosine. So I'll sub in the reciprocal t results. Cosec will be 1 plus t squared on 2t, and cot will be 1 minus t squared on 2t. So let's play with the algebraic fraction here. We end up with 1 on t. Well, that's cot. So remember we said t was tan, reciprocal of tan, cotan. So again, we've solved that we've solved that trig expression by converting it into algebraic fractions and playing with that. All right, so 17F are our t results.